Welcome to your second video for week 12. This is Physics 235, week 12, day 2, scheduled for release on April 8. And today we're going to be talking about dispersion, Huygens Principle, and polarization. So first, dispersion. Dispersion is the process that produces rainbows. It is the splitting or spreading out of white light into its component colors, where white light is a combination of all of the colors of light at once. And it is the process of dispersion that causes rainbows to happen. So, in order to see exactly what's going on, I want to talk us through an example. So in this example, I want you to imagine that you are underwater, hopefully with some sort of scuba apparatus so you can breathe, and you want to send a message to a nearby submarine using a laser. You have a red laser, a blue laser, and a green laser. And if you want the message to get to the submarine the fastest, which of the lasers should you use? So let me type that up for everybody. And we're going to handle this kind of similar to how I would actually run this exercise in a class. So what I want you to do is to take a guess right now between the following options. So the red laser, the blue laser, the green laser, or it doesn't matter. They all take the same amount of time. So take a second to think about this and come up with a guess. Even if you have nothing on which to base your guess and it is truly a guess, the act of taking a guess helps you remember the answer later. So what I want to do now is bring back that image I had earlier of the prism to kind of give you guys a hint here. So I'm just going to draw it by hand. We have white light coming in, making some angle with the normal. And we could see from the cover of Pink Floyd's Dark Side of the Moon that the red, the blue, and the green ray each travel in slightly different directions within the prism. So I'm going to draw these to the best of my ability like this. And then each of these rays then exits the prism, having split into their component colors. So I want you guys now to think about what this process tells us about the index of refraction of the prism. The fact that when white light hits this front edge of the prism, it starts to split into its component colors. So the index of refraction is what determines how much light bends when it passes from one material into another. And we can see here that red, green, and blue, and indeed all of the colors of the rainbow, have all bent different amounts. So what does this mean about the index of refraction of the prism? It turns out that it means you get a different index of refraction for that prism for different wavelengths of light or different colors of light. So with this hint in mind, I want you all to think through this problem and take another guess. See if it's the same one as your first guess. See if you're more confident in your answer this time around. The next question I want you to consider is which index of refraction is higher in the prism, the red, the blue, or the green? Take a moment to think through this. It will turn out that the more the path of the light ray bends, the larger the change in the index of refraction. So since we're having this white light enter the prism from air with an index of refraction of 1, that means the light ray that bends the most must have the highest index of refraction. So this means that the index of refraction for blue, which bends the most, is greater than the index of refraction for green, which bends a medium amount, which is greater than the index of refraction for red, which bends the least. And all of these are within the prism. So think through what this means and take one last guess at this clicker question here. The last thing you need to know to answer this question is to remember that the index of refraction is related to the speed at which a light ray travels in that particular medium. So if we rearrange this equation, we get the speed that light travels in the medium is equal to c divided by n. So if we want the largest speed, we want the smallest index of refraction. So this means we need to choose the laser that has the smallest index of refraction, which is red. So the red laser will get there the fastest, and this is the correct answer in this situation. Now, if you've looked up the index of refraction values for red, green, and blue in the textbook, you'll see that they're not very different. They're very, very close together, just slight differences. So there wouldn't be a significant difference in the amount of time that light takes to reach the submarine with the 3 different lasers, but red would get there first. So dispersion happens because the index of refraction depends on the wavelength. This is one of the reasons that we don't frequently use white light in fiber optic cables, because the signal carried by the red portion of the light would reach its destination before the signal from the blue portion of the light. So usually fiber optic cables are used with lasers, which have only a very small range of wavelength values, so the information stays coherent and arrives all at the same time. This is also why we get rainbows. So I have here 2 pictures from your textbook that I want to explain to show how rainbows happen. You might notice that you can only see a rainbow when you're looking not directly towards the sun, but usually away from the sun. That's because the process that creates a rainbow from water droplets in the air actually involves a reflection as well. So the sunlight, the white light from the sun, comes in and strikes the water droplet and refracts, but the red light and the blue light refract different amounts. So we're going to deal with red and purple because they're at the ends of the spectrum. So red bends the least, and purple bends the most. And then at the back side of this water droplet, we have total internal reflection that occurs. So the red ray is reflected down that way, and the purple ray is reflected this way, and then each of them refract one more time as they exit the water droplet. And the light has now been dispersed into its component colors. You see red at the top of the rainbow and blue and violet at the bottom of the rainbow based on this picture here in the middle. For a water droplet further up in the air, this one, well, it's scattering violet in this direction and red in this direction. The red is what reaches your eyes. But for a droplet further down, it's also scattering violet and red at the same relative angles, but now it's the violet light which is making its way to your eye. So you see red at the top and violet at the bottom. Indeed, whenever you see a rainbow, red will always be on the outside of the arc. And rainbows make an arc because this angle theta that they've labeled in here, that I'm going to kind of try to highlight in green, which is the angle between the incoming light rays and the red that is coming towards your eyes, the arc shape makes it so all of these angles are the same, and then you see a rainbow or maybe even a double rainbow. So there's an extra step of reflections that happens to cause the double rainbow effect. The next thing we're going to talk about is Huygens Principle. And Huygens Principle is useful for explaining some of the phenomena we see in the ray model of light in terms of the wave model of light. And to explain what Huygens Principle actually says, I'm going to need to introduce a term. And that term is a source of wavelets. So if you have a source of wavelets, You can think of this as something that is creating light rays or creating light waves if you prefer to think about it that way. Not unlike if you have an inner tube on a pool and you kind of bounce up and down, you are now a source for water wavelets, and the waves will spread out from you in every direction. And the same thing happens with a source of wavelets. So the source is here in the center in black, and the wavelets are expanding out in a circle, or technically a sphere. Now this is a slightly different way of drawing a wave than what we've seen before. What you actually see here, these lines, are the crests of the wave. So if we look at this image from your textbook, seen from above is kind of what we're looking at, where those blue lines correspond to the peaks of our wave at any given location. So the second picture is kind of the side view, the more formal, like you just plot cosine on a graph view of a wave. But overall, kind of both of these things are happening. So there is actually some displacement up and down, but there's a little depth to things as well. So knowing what a source of wavelets is, just a location from which expand concentric spheres or circles of wave crests, we can now state Huygens principle. Huygens principle states every point on a wavefront is a source of wavelets, and the new wavefront is tangent to those wavelets. So I want to show you how this works with a simple situation first, where we just talk about a plane wave. Plane waves are waves like ocean waves, where they travel in one long line continuing to move in the same direction. So for this plane wave, I want to draw the wavefront we have. So this is just one individual crest of a wave, drawing a line around it. So now Huygens principle tells us that every point on this wavefront is a source of wavelets. So we could imagine this point as a source of wavelets, and the wavelets will expand out from there in a circle. And we can imagine this point as a source of wavelets, and the wavelets expand out from there. And this point is a source of wavelets. And this point is a source of wavelets. And this point is a source of wavelets, and so on. So let me adjust my picture just a little bit here. And now our new wavefront is tangent to all of these wavelets. So we draw a line that is tangent to all of those wavelets. And now this is our new wavefront. And if we repeat this pattern, we will get a picture that tells us how this wave progresses over time. So the next wavefront for a plane wave would be here, then here, then here, then here, and so on, continuing straight lines as the wave progresses to the right over time. Now your book attempts to explain reflection in terms of Huygens principle, and they use what I think is one of the least helpful diagrams in your entire textbook in order to do so. I am going to skip explaining reflection in terms of Huygens principle and just go straight to refraction. So for refraction, we know that the light ray comes in at some angle to the normal and will bend, we'll say, closer to the normal if we assume that n2 is greater than n1 here. So this is standard refraction that we could use Snell's law for. And when you see the ray model, what you want to remember is that all of your wave fronts are perpendicular to the path of your ray. So I'm very specifically stopping these wave fronts at the surface that is the border between n1 and n2. So the light ray comes in traveling this direction along the direction of that red arrow, but our wave fronts are perpendicular to that. Another way of thinking about it is imagine these are like ocean waves. the ocean waves are parallel to the shore, but the waves are coming straight towards you. So if you drew a line along the crest of the wave, that would be perpendicular to the direction the wave is traveling. So when we are out here in N1, any given point on one of these wave fronts is a source of wavelets. So this point might create a wavelet out like this. And this point would create a similar wavelet out like this. And then we get our new wavefront. But my question is, what happens when we are in index of refraction 2 in the other material? So let me draw a couple more wavefronts here. Well, we know that these wavefronts are going to have to be perpendicular to the refracted ray within N2. So this means that our wavefronts themselves actually bend when they enter this other material, say water, so that again the wavefronts are perpendicular to the path of the light ray. So in terms of Huygens principle, each of these points along the wavefront are also sources for new wavelets, and the new wavefronts are tangent to those wavelets. The difference is that these little green circles are smaller than these purple circles, and they're smaller because the light travels slower in the higher index of refraction medium. So since the light travels slower, this means the wavelets themselves also spread out slower. So our wavelets actually expand at whatever the speed of light is in that material. And it is this slowing down of the wavefronts and the slowing down of the waves because of the index of refraction that you get the bending of light from refraction. Now, I expect you all to understand Huygens' principle in theory and be able to explain it to me in words, but if you'd rather think about refraction in terms of Snell's law and not worry about this Huygens principle wavefront nonsense, then that's perfectly fine unless you're a physics major. So if you're planning to be a physics major, I recommend getting comfortable with Huygens' principle. There's also one more aspect of Huygens' principle that is relevant here, and that Huygens' principle is why waves spread out around corners. So let's make ourselves a corner or an opening. So we will have something that is blocking most of the light that's coming in here. Maybe some small slit cut in a piece of paper and we shine a flashlight at it. So the wave fronts, as they make their way, say a plane wave, up to the opening, eventually some of them are blocked by whatever this is that we've created the opening in. So only little bits come through at the beginning. And you might think that the waves continue on like this, but Huygens' principle actually says otherwise. So each point on the wavefront is a source of new wavelets. So we could label this point here in red, and it is a source of new wavelets. And so is this point right here. So now our new wavefront is flat in the middle, but bends a little at the edge. Then we can draw the Huygens principle process again, because right here we would have a wavelet. Here we would have a wavelet, and you can draw as many of these as you want to until your diagram gets too complicated. Oops, it's not big enough. So now our wavefront, still flat on the front, but curves even more around to the sides. And if you keep repeating this process, you will get wavefronts that look a lot like this, spreading out around the corners. Now, exactly how much the waves spread out depends on how big the opening is and the wavelength of the light. If the wavelength of the light is much, much smaller than the opening it's passing through, then there's not much spreading out that happens. If the wavelength of the light is similar to the size of the opening, you'll get much more spreading that happens. And we're going to explore this phenomenon later when we talk about the double slit interference experiment and the single slit interference experiment. And the fact that light spreads out around corners, and sound, it's also a wave, so sound will also spread out around corners, is very good for us. Because if it didn't, that would mean we would need to have direct line of sight to someone in order to communicate with them. And the last thing I want to talk about today is polarizers. And to talk about this, we're going to need to go back to our idea of light as an electromagnetic wave. So I'm not going to draw the magnetic field parts, just the electric field parts. Now we drew our diagrams nice and even where the electric field was along the y-axis and the magnetic field was along the z-axis. But in real life, those can be oriented however they want to be as long as they're perpendicular to each other. So in what we will call unpolarized light, the electric fields are pointing in every possible direction at once. So some of the photons might have their electric field oscillating up and down, some of them might have their electric field oscillating left and right, and every angle in between. So what we're going to do is we're going to send light like this, which is referred to as unpolarized light, into a material called a polarizer. And the polarizer has something called the polarizer axis. And the effect that this has on the light, so this light comes in, and then coming out of that polarizer, we will be left with light that only has electric fields oscillating up and down. Only light with the electric field along the polarizer axis is allowed to pass through the polarizer. So now, this light that we have, where all of the electric fields are aligned in the same direction, this is called polarized light. And this will have an effect on the intensity of the light. So when unpolarized light passes through a polarizer, your new intensity of the light after it passes through the polarizer will be precisely half of the original intensity. So this is what happens when unpolarized light hits a polarizer, but what happens when polarized light hits a polarizer? So let's say we have light that is polarized at an angle, like this. Let's actually make that angle even more extreme. And we're going to send that polarized light through the same polarizer, with the polarizer axis oriented up and down. So only light with its electric field parallel to the polarizer axis will pass through the polarizer. But here it turns out this light is not going to be completely blocked. We will have some of this light that gets through. And I want to show you precisely how much. So what's happened here is we have less electric field than we had before in terms of magnitude, but it's all polarized along the polarizer axis. And what's happened here is that one of the components of the initial electric field has been eliminated. We could refer to this component as E parallel, the component of the electric field parallel to the polarizer axis, and this is the part that survives. Also have this other component of the electric field, the component of the electric field that is perpendicular to the polarizer axis, and this part is completely blocked. So in words, only the component of the electric field parallel to the polarizer axis will pass through the polarizer. And in terms of intensity, our new intensity is going to be related to the old intensity based on the following formula. The new intensity is going to be the original intensity before the polarizer times cosine squared of theta. And this angle theta here is the angle between the polarized light and the polarizer axis. So here, this angle will be theta. So there's a couple applications of this that are relevant for everyday life, because you've actually probably seen polarized screens and polarized glass without maybe even realizing it. Nicer sunglasses are usually polarized, and they're polarized for the following reason. So here's a picture from your textbook, and we have unpolarized light with every possible orientation of the electric field in there. And when that light reflects off of a surface, it turns out that that reflection and the corresponding refraction don't occur evenly between the different orientations of the electric field. With the light that is reflected from a surface, in this case, the vertical components of the electric field, the part that is perpendicular to the surface they reflected off of, are going to be diminished. So light, after it reflects off of a surface, mostly has a polarization that is parallel to the surface. So coming off of this reflection, we have light that is, we'll say, horizontally polarized. So when you have your sunglasses, if we have sunglasses with a polarizer axis that is vertical, this means that most of that reflected light will be blocked out by the polarizer that is our sunglasses. So this is why when you put on polarized sunglasses, a lot of the glare that you see coming off of light reflecting off of cars and off of the street and off of water is greatly diminished. And then you can see more clearly into a pool. So if you have a pair of polarized sunglasses, go out on a sunny day to some body of water and look into that body of water with your sunglasses off, and then put your sunglasses on, and you'll see that you can see much more clearly into the water with those sunglasses on. So I do want to do one example real quick before we call it a day, and it's related to an interesting phenomena that you can have with polarizers. And I was going to demonstrate this in person, but I do not have any polarizing film available to make this demonstration myself, so you're going to have to make do with me talking you through it on this video. So we are going to send in unpolarized light into a series of polarizers and find out how much of the original intensity makes it through. And we're going to consider two different scenarios here. In the first scenario, we will begin with our unpolarized light, and we are going to send that into two polarizers. The first polarizer is going to have a polarization axis that is horizontal, that we are going to call 0 degrees. And then the second polarizer is going to have a polarizer axis that is vertical. So we'll say that's an angle of 90 degrees. So let's see what happens. If this original light has intensity I0, then after the unpolarized light passes through a polarizer, we know it will have an intensity of I0 divided by 2. We also know that the light that makes it through will have a polarization of its electric field that is parallel to the polarizer axis. So since our polarizer axis of this first polarizer was oriented at 0 degrees, horizontal, then the electric field that survives is also oriented at 0 degrees, or horizontal. And now this electric field, this polarized light, is going to pass into our second polarizer. So our new intensity here at the end is going to be, not there. So our new intensity is going to be the intensity that comes into the polarizer, which is I0 divided by 2, times the cosine squared of the angle between the polarized light and the polarizer axis. Well, the light coming in as its electric field oriented like this. So we need to find this angle here between the polarizer axis, which is vertical, and the polarization of the light, which is horizontal. And this is a right angle. So we need the cosine squared of 90 degrees. So cosine of 90 is 0. So cosine squared of 90 is also 0. So we end up with an intensity of 0. None of this light makes it through. So if you hold two polarizers up on top of each other with their polarizer axes at 90 degrees from each other, none of the light will pass through. It will completely block all incoming light. So for the second half of this problem, I want to take the same exact setup with only one change. So we still have our unpolarized light at the beginning, and it's still going to have an intensity of I naught. We're still going to send it through our first polarizer with a horizontal polarizer axis at 0 degrees. But then, before we get to the 90-degree polarizer, we're going to add another polarizer that is polarized at 30 degrees, where that 30 degrees is this angle right here. And then after this polarizer, we will send the light through the vertical polarizer, oriented at 90 degrees. So again, this is the exact same situation as before. We've just put a new polarizer between the original two. And something a little weird happens here. So let's work through. So first, we have unpolarized light hitting a polarizer, and this will be the same process as before. We will end up with half the intensity we started with, and our light will be horizontally polarized. But now this horizontally polarized light is going to be sent into this polarizer with a polarizer axis oriented at 30 degrees. So the light that we have left afterwards, our intensity after this polarizer, is going to be the intensity that comes in, I naught over 2, times the cosine squared of the angle between the polarizer axis and the polarization of the light, which is this angle right here, which is 30 degrees. Well, the cosine of 30 degrees is square root of 3 over 2. So if we square that, we get 3 over 4. So the light that makes it through has an intensity of the original I naught over 2 times 3 over 4, which turns out to be 3 I naught divided by 8. So the intensity of our light has gone down. But now I want you to think about what kind of light comes out of the second polarizer. Well, polarized light always comes out of polarizers, but specifically light that is polarized along the polarizer axis. So the light that comes out of this second polarizer is oriented at 30 degrees from the horizontal. And now this is the light that is going to enter into our last polarizer. So we have polarized light that makes an angle of 30 degrees from the horizontal that is entering this last polarizer. So our new intensity will be whatever intensity came in, which was that 3 I naught over 8, times the cosine squared of the angle between the electric field polarization and the polarizer axis. So we want this angle right here, which is 60 degrees. Cosine of 60 is 1/2, so cosine squared of 60 is 1/4. So this gives us, we still have the 3 I naught over 8, the intensity of the light that came in, times 1/4. Our final intensity here then is 3 I naught divided by 32. So we only have around 10% of the original intensity of the light that gets through this whole process, but some of the light does make it through. And the light that does make it through will have its electric field oriented vertically. the same as the most recent polarizer it passed through. So note the differences between these two cases. In both of them, we have two polarizers that are perpendicular to each other, but in case B, we had an intermediate polarizer in between. So if you have two sheets of polarizing paper that are oriented perpendicular to each other so that no light is getting through, and you slide another sheet of polarizing paper or polarizing film between the two of them, now some of the light does make it through. So it's just an interesting application, and it usually is a little surprising and counterintuitive to people, so I figured it would be a good example to go through. That's everything I have for today. I wish we could have done this one in person because there's a lot of useful equipment and demos that I plan to do on this day. So I've done the best I can with this video, but please don't hesitate to reach out to me for individual office hours appointments or come to the group office hours that I hold every Friday at 10 a.m. if you want to ask further questions and be able to talk to me in more of a back and forth situation rather than me just talking at you through these videos. That is everything I have for today. Thank you for watching, and have a good day.